Hello, my name is Oshit Chaudhary and I worked on Design MS5 and I worked with the group members' names on the slide. Here's an image of our group. This assignment aims to design a quark crystal microbalance that can accurately measure the thickness and constituent elements of thin film deposit on a sensor. The QCM will have bridge structure composed of titanium and single crystal X quartz with a window in the middle for film deposition. The project will optimize dimensions of QCM bridge structure, including the length, width, and thickness, as well as thickness of each stratum. The sensitivity of the QCM will be tested for different coating materials, including gold, molybdenum, chromium, and quartz glass to determine the expected longevity and actual sensitivity versus thickness for each material. The goal is to obtain the most extended lifespan possible and push the device sensitivity limit. I primarily focused on writing the report. The problem of optimizing a quartz crystal microbalance to maximize its sensitivity can be achieved by reducing the number of variables and identifying optimization through relative thickness ratio between the quartz and titanium layers can be determined using the stiffness matrix for quartz, the Young's modulus in the X direction, and the Young's modulus of titanium. By plotting the relative curvature against the ratio of thickness, the maximum curvature and thickness ratio can be found. The length and thickness of QCM can further be optimized, and with the width can be ignored, resulting in only thickness and length of the window as the variables to sweep through. The problem can be solved using model analysis, looking for the first mode as the resonant frequency. The code can be set up similarly using the design SM4 and with minor modifications. The model developed for QCM resonator can be validated through several methods. Firstly, the piezoelectric portion of the resonator can be validated by running electric current through it and observing the resulting vibrations at a particular frequency. The frequency should remain constant regardless of changes in the voltage, but can be affected by the material properties and thickness of the layers. Secondly, the structure aspect of the model can be confirmed by fixing one end in the y direction, allowing X section to be free to slide, as seen in the plot. The titanium layer of the piezoelectric can also be validated, as its thickness will cause reduction in the frequency of the resin. Finally, the deposit material is free to deform, but also must be attached to the side of the quartz. There's no constraints present on it, and this is evident from the plot. Overall, the validation methods provide confidence in the accuracy of the model developed and suggest that it can be used to simulate behavior of QCM resonator under various conditions. The Maple code constructed validated the model corroborates with results from FlexPD within a certain degree. The validation methods outlined confirm the model is accurate and can be relied upon for further analysis. Moving on to optimization, we modified the existing code slightly as seen in the images here. The lines in the FlexPD code have placeholder index values corresponding in the elements in Python list. The necessary modifications involving changing the values for the length and thickness of the window, as well as the output file format in the FlexPD script. The FlexPD code now modified is integrated in the Python code, which is split into various modules for future design tasks to sweep over the acceptable values for window length and thickness. Constraints were used to generate a range for the length, while an arbitrary value was used for the thickness. Using the NumPy module, 9 data points were created for each range in the successive runs of the program, zooming in and obtaining sensitivity for each value. Although 2D plots of thickness against the sensitivity were attempted, curve fitting was not possible in the allotted time. The plots showed an exponential drop-off with increasing thickness, which is expected. From here, the code was made to sweep through the data points and obtain optimum values, but before feeding values to FlexPD, they were rounded as stated earlier due to problems with the end grid. Once the sweep was complete, running into multi-thread fashion to aid speed, the data was then collected and plotted as on a 3D axis for viewing, and brief summary for each code file can be seen in the flowchart on the slide. The optimization process involves zooming into 5 data points from previous runs that yielded sensitivities and using them to span a new range of thickness and lengths. Multiple iterations were done for each material, and the range was progressively zoomed in to a point where it was less than 300 micrometers. The maximum value was marked with green triangle on the plot, and a legend was added. Curve fitting and identification of the point where the QCM would no longer have an acceptable sensitivity were explored, but not completed within the allotted time. Results of the optimization process are shown in the next few slides. So in this slide, we see our maximum for gold. In this slide, we see our maximum for molybdenum. In this slide, we see our maximum for chromium. And in this slide, we see our maximum for quartz. In summary, a design for a quartz crystal QCM has been developed using finite element analysis and validated through experimentations. The Python code was developed to sweep through acceptable values for the length and thickness of the window for each deposition material, using a modified FlexPD code to output the resonant frequency in text file. The code was compartmentalized into multiple modules to allow for easy repurposing, and a sensitivity analysis was conducted to determine optimal window thickness. The simulation results showed that some materials exceeded the acceptable sensitivity threshold while others did not, but further optimization with curve fitting and grid search could improve the results. However, limitations such as rounding and floating point errors in the raw data and the use of 2D simulations instead of a 3D simulation were present. Despite these limitations, the simulation is still usable with a reasonable precision, but could be improved with optimization given more time. Thank you.